We're delighted to have Ashoke Sen from ICTS Bengalore, who's going to tell us about the supersymmetric index of small black holes.
Okay, thank you. And I'd like to, first of all, thank the organizers for inviting me here and to this excellent workshop. So this is the title of my talk today, Supersymmetric Index of Small Black Holes. And what I'm going to describe is essentially contained in this paper over here. Okay. And then there is also related work by Chen, Murthy, and Turiachi. And I think Samir is going to talk about this in the afternoon. Okay. So let me begin by recalling some general facts about black holes. Okay. So we'll be starting our discussion with black holes in two-derivative theory of gravity in d dimensions. Okay. And in general, the black hole can carry a set of U1 charges depending on whatever many U1 fields you have. It can carry angular momentum in the Cartan subalgebra of SO d minus 1, okay, which could be more than 1 if d is larger than 4. Okay. And it's also characterized by its mass. Okay. And the Bekenstein-Hawking entropy of the black hole has this form. It's given by the area over 4 times the Newton's constant. Okay. And this you can re-express as a function of the charge, mass, and angular momentum. Okay. And I remind you again that Q and J in general can have multiple components. Now, as I said, we'll begin with a two-derivative action. Okay. And two-derivative actions have a nice scaling property. Okay. So we'll be considering fields where you have the metric, the two-form field, massless two-form field, the gauge fields, and scalars. Okay. Now, if we scale the fields in this way for some arbitrary real parameter lambda, okay, then the action scales as lambda to the d minus 2. Okay. So the lambda to the d factor comes because there is a square root of determinant g in the expression for the Lagrangian density. And the minus 2 comes because with two derivatives, you need a inverse metric to contract those two derivatives. So that gives you lambda to the minus 2, right? So that's where the origin of this lambda to the d minus 2 is. Okay. And because of the scaling property of the action, the black hole entropy also has a simple scaling property. Okay. Again, this is a two-derivative theory where the Bekenstein-Hawking formula is valid. Okay. And the scaling property takes this form. Okay. That if we scale q, m, and j by these powers of lambda, the entropy scales as the action, which is lambda to the d minus 2. Okay. And because of the scaling property, there is a nice way to take the macroscopic limit. Okay. We simply scale m, q, and j by these powers of lambda and take lambda to be large. Okay. This way, basically, all terms in the entropy scale in the same way, and the black hole entropy scales as lambda to the d minus 2. And the general goal that we have been following for many years now, okay, is to compare the entropy that you calculate this way, okay, and its higher derivative corrections that I'll be mentioning later, with log of degeneracy from some microscopic counting of degeneracy of states. Now, we also introduce chemical potentials. These will be important for us later. Okay. And I'll call all of these as chemical potentials. This is the inverse temperature, okay, which is the derivative of the the Bekenstein-Hawking entropy with respect to the mass. This is a chemical potential for the charges. And this is what is also sometimes referred to as the angular velocity. This is a chemical potential dual to the angular momentum. Okay. And mu and j, mu and omega, will also have multiple components because q and j have multiple components in general. Okay. And it follows from the scaling property that I described earlier that beta scales as lambda, mu scales as 1, and omega scales as lambda inverse. Okay. And these are important because in an Euclidean gravity path integral, these set the asymptotic boundary condition, and these are taken as independent variables. So instead of taking the mass, charge, and angular momentum as independent variables, in the Euclidean gravity path integral, it's more natural to start with these as being specified as independent variables. And the final ingredient that I'm going to that I have to review is that the Bekenstein-Hawking formula works only at the level of two derivative action. Once you take into account higher derivative corrections, then you have to use Wald's formula, and these give correction to the entropy from classical higher derivative terms, and as a result, the scaling properties are modified. Yes.
And Ross from the 90s that says that the boundary conditions for a magnetically charged black hole are such that you fix the charge.
Yes, yes, indeed. So here Q refers to electric charge. I will not consider magnetically charged black holes, indeed.
Thank you. Yeah.
Sorry, maybe a naive question. If I consider supersymmetric black holes, how is scaling being consistent with the BPS bound?
It's the same scaling, because this scaling comes only for the bosonic part of the action, right? And supersymmetric black hole entropy also scales in the same way.
Because if I look at the mass, it scales slower than the spin. So, but
yes, because J, if you look at the mass indeed does scale lower than the spin. For supersymmetric black holes in 4 dimension, of course, there is no the spin is 0, right? You don't have spinning. In 5 dimension, there is a spin. But spin and mass scale differently, right? Because if you remember the BMPV black hole entropy formula, it's square root of Q1 Q5 n minus J square. So Q and J scale differently, and the mass scales as Q, right? So that's this follows. I mean, this formula here that I've written is consistent with that scaling. Okay. Is that clear? So mass and angular momentum don't scale in the same way.
Okay.
Yeah.
Oh.
Okay, so this formula that I mentioned, entropy is log of degeneracy. Okay. This indeed has been tested in many examples in string theory. Okay. However, there remains one open issue, okay, and that is the following: that when you compute the degeneracy, okay, the microscopic degeneracy, this is done by representing the black hole states as states of some brane system carrying the same charge as a black hole. That's how you identify that this is the particular system whose entropy should be compared with the corresponding black hole entropy. Okay. But the dynamics of these branes is understood as weak coupling, and this is where the counting is done. Okay. In fact, one basically uses the free field limit, okay, and in that case, the dynamics of the branes just reduces to a collection of harmonic oscillators, and that's what one uses to count the number of microstates. But the black hole description is valid only when the gravitational coupling is strong enough so that the horizon size exceeds the component radius. Okay. So these are different regimes in which the analysis is done. And so the question that arises is, how can you compare the two expressions? Okay, because you are comparing a calculation at weak coupling to a calculation at strong coupling. Okay. And the answer that is given tentatively is that we try to compare supersymmetric index of BPS systems, and the reason is that this is similar to degeneracy, okay, and it does not change as you vary the coupling constant. Okay, so if we can calculate the supersymmetric index on both sides, then indeed it is possible to compare a weak coupling result to a strong coupling result, because the supersymmetric index doesn't change. Now, on the microscopic side, the calculation of the supersymmetric index is reasonably straightforward, okay, because as I said, we really have a collection of harmonic oscillators. Okay. So supersymmetric index basically means that you have to calculate the number, not just the number of states, but number of states weighted by -1 to the f. Right? That's as easy as calculating the degeneracy. But on the black hole side, of course, we know how to calculate the entropy, and entropy measures degeneracy, not the index. Okay. And here the assumption that is typically made in this comparison is that index and degeneracy are equal at generic coupling. So even though on the black hole side we calculate the degeneracy by entropy, we expect that at a generic coupling that is the same as the index, and hence we can compare the two. Okay. And there is some justification of this, okay, based on the near horizon ADS2 geometry and supersymmetry. Okay. But this is subject to corrections by modes living outside the horizon. Okay. So this justification holds only for the modes in the horizon. If there are modes living outside the horizon, then that argument fails. So this leads to the question that is it possible to do better by computing the index also on the black hole side? On the microscopic side, you know how to calculate the index. So is it possible to calculate the index also on the black hole side? So this brings me to the subject of supersymmetric index. So I'll now explain what is it that we try to compute. Okay, what is supersymmetric index, and then I'll tell you how on the black hole side we go about calculating the index. So let's consider a supersymmetric theory in d space-time dimensions. And we now denote by J the angular momentum in a particular two-dimensional plane. Okay, earlier I said that angular momentum can have many components, but now let's focus on angular momentum in a particular two-dimensional plane. And the supersymmetric index is defined in this way. So this subscript q k equal to 0 means that we take the trace over all states at fixed charge. Okay, so all states carrying a fixed charge. This is again electric charge, magnetic charge I am setting to 0 anyway. And 0 momentum. Okay. And what you compute, what is enters the trace is e to the minus beta h. This is the standard time evolution operator, Euclidean time evolution operator. This is minus 1 to the f, e to the 2 pi I j. And then we also put in a factor of 2j to the n. Okay, I'll explain why this is needed. Okay. So one can show that if we calculate a trace like that, it gets contribution from only those states that break 2n or less supersymmetries. Okay, and these are what we call BPS states. Okay. So for example, if n is 0, okay, then this means that this trace will get contribution from only those states which do not break any supersymmetry. Okay, and those are only the ground states. Okay, so n equal to 0 is a Witten index that just counts supersymmetric ground states of the system. Okay. If you are trying to calculate supersymmetric particle-like states, okay, we have to allow n to be non-zero. Okay. But for appropriate choice of n, okay, we can ensure that a generic non-BPS state will not contribute because it breaks all supersymmetries. Okay. But BPS states, okay, which break less than 2n supersymmetries, okay, will contribute to the index. Okay. Yes.
My confusion, just to put it in a frame or understand. Yeah. So, for example, when you have an ADS2
yes.
states, then you have ground states. So the states when you have an ADS2 theory, you're counting ground states. So those should be states which don't break any supersymmetry.
Yes.
But the same states, if I put them in the D1D5P system, for example, they're momentum carrying states. So then yes. They should, in that frame, those states should be breaking.
Yes. So okay. There you have to put this 2j to the n. Okay.
Sorry?
There you have to put this, there if you want to count the same states from the asymptotically flat viewpoint, then you have to put this 2j to the n factor. Okay. And the reason is that if you think of this as asymptotic, black holes embedded in asymptotically flat space-time, it breaks certain space-time supersymmetries. So there are fermion zero modes, right? And those fermion zero modes live outside ADS2. Okay.
I see.
So if you don't put this 2j to the n, then the trace over those fermion zero modes will just make the answer vanish.
So in flat space, you have to put the 2 to the n, and then when you go to ADS2, then you basically then you're counting ground states, and then it's
then you don't put 2j to the n. Indeed.
Okay.
Yes.
Thanks.
Okay, but we will be considering today the from the viewpoint of asymptotically flat space-time. So you have to put this 2j to the n. Okay. But as we'll discuss, this has a very trivial role to play. Okay, so this is what I have said here. Okay. So this 2j to the n factor, right, this is put in the trace because as I said, if you don't put the 2j to the n, then the BPS states also don't contribute to the trace, only the ground state contributes. Okay. There is also a similar understanding from the point of view of the gravitational path integral, okay, namely that the gravitational path integral has some fermion zero modes, and this 2j to the n basically soaks up those fermion zero modes. Okay, otherwise it really has no role to play. Okay. So this 2j to the n is necessary, but its role is somewhat trivial. So just to simplify our writing, okay, we'll just drop this from our formulae. Okay, we'll just not write it explicitly, but it should be kept in mind that this 2j to the n is there in every trace that we'll be ever encountering, and all it does is that it just soaks up the appropriate fermion zero modes in the trace. Okay, so on the microscopic side, we can, well, easily in quotes, okay, but we can compute the index in many, say, for many systems. Okay. And what it does is it counts the number of BPS states with some weights, right? So this is the index again. Okay. So 2j to the n have dropped, right, because that just provides some kinematic factors. Okay. So when you take the trace, okay, because you have this -1 to the f, it gets contribution from BPS states, okay, which means that H is set equal to the BPS mass formula. Okay, H it gets contribution from only states of a particular energy, which is m BPS, okay, and then it just counts the total number of states with which saturate the BPS bound, and that's what I'll call e to the s BPS. Okay. So this will be the definition of e to the s BPS. S BPS is basically the log of the index rather than the log of the degeneracy, right? Because this is how you have defined s BPS. Okay. So what we want to do is to compare this with the results from the black hole side. Okay. So if we want to do that seriously, then we should also calculate the index of the black hole states. Okay. And this is what I'm going to describe now. How do you calculate the index for the black hole states? Yes. No, at this stage, I have not made any commitment to any particular string theory. Right? This discussion is valid in general. Any other question? Okay. So let me now review some aspects of the gravitational path integral, because that's what you are going to use to compute the index. I think I missed one. Yeah. Okay. So you define the gravitational partition function, okay, as a result of the path integral over all fields weighted by exponential of minus action, standard path integral. Okay. But we subject it to the following asymptotic boundary conditions. Right? And this is where the chemical potentials that I introduced will come into play, okay, because they are the ones which set these asymptotic boundary conditions. So first of all, we do this path integral in the Euclidean space-time. So the Euclidean time tau and the azimuthal angle phi, okay, there are many angles in general, right, because as I said, we have SOD minus 1 rotation group. Okay. So these are periodically identified in this fashion, right, that when tau goes to tau plus beta, and at the same time we take phi to phi minus I omega beta, then these should be identified. Now this I may bother you, but it's only temporary, because soon I'm going to set omega to be imaginary, right? So it should be completely real analysis. At the same time, the time components of the gauge fields take a particular form of the asymptotic values, and that's given here. A tau should be minus I mu. So mu again is a multi-component object because there are multi-component gauge fields, right? There are more than one U1 gauge fields in general. So the idea is that this path integral, okay, is dominated by the Euclidean black hole saddle point, whose chemical potentials are given by beta, mu, and omega. Okay. And log z is given by minus the action at leading order, right, because of this fact that the weight factor e to the minus action, that gives a dominant classical contribution, and there are corrections. So this is one side of the story, the gravitational side. On the other hand, we can also give it a statistical interpretation, okay, namely what the z computes is trace of e to the minus beta h, right, this is the standard time evolution operator, and you also have minus beta mu dot q and minus beta mu dot omega dot j. These come because of these twisted boundary conditions that are given here and the boundary condition of the gauge fields that we have put here. Okay. So if we expand out the trace, we see that what it computes is the sum over all charges, angular momenta, mass, and the momentum, okay, weighted by these factors e to the minus beta m. See, h I have now written as m plus k square over 2m, because the black hole mass I am assuming to be large, so the non-relativistic formula is good enough. Okay. Then you have minus beta mu dot q minus beta mu dot j, and then the trace just picks up the total degeneracy of states with these quantum numbers. So that's what I'm calling as e to the s exact MQJ. So e to the s exact by definition is the total degeneracy of states carrying quantum numbers m, q and j. Okay, at this point I have not made any approximation. So we now examine these two different descriptions of Z again. So this is a statistical description, okay, which I had written down earlier. And this sum here, okay, just in ordinary statistical mechanics, whenever you have a ensemble sum like this, okay, so this is the grand canonical partition function. This e to the s exact, you can think of this as a microcanonical entropy. Okay, and this is a change of ensemble from microcanonical ensemble to grand canonical ensemble. Okay. So this sum will be dominated by the contribution from the saddle point of this sum, okay, where this is extremized with respect to m, q and j. Okay. And by evaluating this at the saddle point, we get log of z as s exact minus beta m minus beta mu dot q minus beta mu omega dot j. That's the leading classical part or leading contribution from the saddle point. And then there are fluctuation terms, right? Because you have to compute the one loop determinant of this sum around the extremum, and those typically give rise to logarithmic terms. Just to give an example, right? When you average over k, when you do this sum over k, right, which is really an integral, okay, you will get for every k integral you will get a factor of square root of m over beta, right? And that will appear in the exponent as a log of square root of m over beta, right? Those are what I am calling logarithmic terms. So these log terms come from statistical fluctuations around the saddle point. On the other hand, okay, we can calculate log z by the gravitational path integral. Okay, and so to leading classical contribution, okay, this was in fact, okay, Gibbons and Hawking's result involves the Bekenstein-Hawking entropy formula over here, right? So they derived this formula for Bekenstein-Hawking. Okay, but once you include the hard derivative terms, the Bekenstein-Hawking term gets replaced by the world term, but otherwise it remains the same. So this is the classical contribution to the gravitational path integral. Okay. And here again there are logarithmic terms, but these logarithmic terms come because you have to compute the one loop determinant of fluctuating fields in the gravitational path integral. Okay. So these have different origins, right? These log terms come from one loop determinant of fluctuations in the gravitational path integral. These log terms come from statistical fluctuations. Nevertheless, we can now compare these two, okay, and we see that these terms of course cancel, okay, and we get s exact as s world plus logarithmic terms, some of which come from the gravitational path integral and some of which come from statistical fluctuations. Okay. And this procedure in fact has been used earlier to compute the logarithmic corrections to various non-supersymmetric black holes, right? So far I have not said anything about supersymmetry. This is just standard gravitational path integral. Okay. Now we are going to do something slightly different. Okay. Instead of trying to compute the gravitational path integral, okay, directly, okay, we will try to compute a modified version of the gravitational path integral that gives the index. So let's look at the same statistical expression for z that we had. This is, we said in the previous slide that this was the expression for z that the gravitational path integral computes. Okay. All that I'll be doing now is that I'll choose some particular form of omega. Right? Omega is up to us, right? That sets the boundary condition asymptotically. So I'm now going to choose some particular form of omega. And the form of omega that I'm going to choose is that the first component I'll take to be minus 2 pi I over beta, and the rest of the components I'll set equal to 0. In that case, e to the minus beta omega dot j becomes e to the 2 pi ij. Right? That's the minus 1 to the f that we need. Okay. And then z, okay, now becomes, you see in the case of z, this becomes e to the 2 pi ij. So now you are really computing the index. Okay. So index, if you recall, was defined at fixed values of q and k. sum over J and M, right? J and M are not restricted in the definition of the index. So if we write Z as sum over Q and K, and after you have summed over J and M, okay, we get the index, which is, so you get e to the SBPS Q. Okay, let me remind you the definition of the index. Okay. The definition of the index took the trace over all states, in particular all M and all J, weighted by this factor over here. Okay, and that we identified as e to the SBPS Q minus beta MBPS Q. Okay, so that's what I'm doing here, e to the SBPS Q minus beta MBPS Q, and then these factors are there, e to the minus beta K square over 2 Mbps and minus beta mu dot Q. Okay. This has gone away because this provided the 2 pi ij. Okay. And again, let me emphasize that this 2j to the n factor that we had, okay, I'm not writing it here, but it's there in this trace. It has to be included, otherwise it will just vanish from the Fermion zero mode integral. We can now do a saddle point approximation of this sum. Okay. And we will get log z as s bps q minus beta m bps q minus beta mu dot q. Okay, these terms, and plus log terms. Right? The k is summed over anyway, right? So once you do the sum over k, the saddle point of k is at k equal to 0, and it will provide that square root of mbps over beta factor, right? Which will contribute to the log terms.
If you have multiple J's, then you just specify this chemical potential to what you set.
Yeah. So
for
this
one
is
of the J's.
Pardon?
You set the chemical potential omega to this value for just one of the J's.
Yes. Well, it is.
Or
no chemical. This is a vector, right? I put one of the first component to minus 2 pi over beta.
Oh,
the
I
rest
see.
of the things I am setting equal to 0.
Oh, I see. So you're turning off chemical
Or
potentials
chemical
for
potential.
all
But
the
I should add that, I mean, in general, you can consider a more refined index where you can also turn on chemical potential, right?
Okay.
But I'm not, just for simplification, I'm not doing it here, right? Because for where I'm going to apply it, right, this is good enough.
Okay.
But in general, you can't turn on chemical potential for other J's as well.
Okay, thank you.
In order to get the j to the n from your previous definition of the index, don't you want to take n derivatives with respect to omega?
You could do that,
Okay.
you could do that, right? And then set omega equal to minus 2 pi by beta,
Yes.
or just insert this 2j to the n directly in the path integral, right?
Okay.
But as I said, the main role of this 2j to the n in the path integral is that there are some fermionic zero modes in the path integral,
Yes.
and this 2j to the n helps you soak up the fermion zero modes. Otherwise, the path integral will just give you 0.
So I just want to make a comment because Joseph also asked this question.
Yes.
This insertion of the fermion zero modes is specific to asymptotic flat space.
Yes.
So in gauge supergravity, you don't need to do that because the representation theory of the superconformal index is different. And
Yeah. So in particular, in ADS2, certainly you will not insert these. Yeah. Okay. So this is what we got. That so essentially, this differs from the previous formula that I showed in the last slide, right? This formula, or sorry, this formula over here. Okay. In that, we have just set beta omega equal to minus 2 pi I for one of the components, right? And then instead of getting the log of the degeneracy, you are now getting log of index. That's what this formula is. So we now combine the two results. So this was the gravitational result, right? It's the same gravitational path integral. I'm not doing anything, okay? Except that I'll be eventually putting this beta omega equal to minus 2 pi I. Okay? And this is the result that we got, okay, which captured the formula for the supersymmetric index, because SBPS is the log of the supersymmetric index. Okay. So if we now set omega equal to minus 2 pi I over beta, right, in the first formula, and then this is for one of the components, the rest I'm setting equal to 0, okay, and you compare these two formula, okay. First of all, one would expect that once you set in the gravitational path integral, omega equal to minus 2 pi over beta, okay, it's computing a supersymmetric index. Okay. So it should get contribution only from those saddle points for which the mass is equal to the BPS mass formula. Right? It should get contribution only from supersymmetric ground states. Okay. So you expect that at omega equal to minus 2 pi over beta, we should have m equal to mbps. Okay. And once you set m equal to mbps, we see that all these terms cancel. This cancels this beta m cancels beta mbps. Okay. And but this one doesn't cancel. Minus beta omega dot j is still there. Okay. We have set beta omega equal to minus 2 pi I. Okay. So the formula, so by comparing these, we now get S BPS is S world, okay, plus 2 pi ij plus logarithmic terms. Okay. And this general procedure, okay, was basically spelled out in these papers over here. How to compute the index from gravitational path integral. Okay. So this will be our main formula that we are going to work with. That the BPS black hole entropy, the BPS index is given by the world formula, okay, plus 2 pi aj, okay, plus possibly logarithmic terms. Okay. And so the conclusion is that we can calculate the log of the index by this formula, provided we adjust parameters so that omega is set equal to minus 2 pi over beta. And this formula has been tested in many examples, okay, for a wide class of regular BPS black holes, including logarithmic corrections, okay, both in 4 and 5 dimensions. Okay, and it agrees with the microscopic results. Now, one particular feature of this formula is that on the right hand side, okay, there is one extra parameter compared to on the left hand side, okay, because see on the right hand side the beta is a free parameter, okay, or equivalently j. Okay, we have said beta omega equal to minus 2 pi I, right? So omega is fixed, but beta is still a free parameter. Okay. So on the right hand side you have one extra free parameter, but the left hand side is not supposed to depend on beta, right? Because it's just picking out the black hole index. So this is a non-trivial consistency check, that this combination over here should really be independent of beta. Okay, and that again has been tested in for these black hole solutions. Yes.
These are the states for which there's a mass gap above, is that correct?
Yeah, these are BPS states, so there is a mass gap indeed.
Yeah. So, because one might have been worried that in this m equals mbps relation, that if there were states that were very close to that threshold, say exponentially close as opposed to power law close, then because you're working in a kind of saddle point approximation, you would actually be including states that should not contribute to a proper index because they are not actually supersymmetric states. But the existence of this gap prevents that from happening. So that's a nice relation between these two ideas. Is that
That's
right?
true. That's indeed true. Yeah.
Okay.
So the existence of this gap is what is needed to avoid having that. It's you can cleanly distinguish between BPS and non-BPS states because of this gap. Yeah, indeed. Okay. And in general, the zero mode integrals will kill the non-BPS states.
Just to make a comment, so this what you said can be explicitly checked by doing the super-Schwarzian calculations, the path integral over the super-Schwarzian modes in the gravitational, in the black hole, near horizon of the black hole. Okay, so now I come to the part of the talk that, so this is a general introduction of how to compute the index from entropy, index from black hole entropy in some sense, or index from gravitational path integral. Okay. Now I am going to apply this, okay, to the specific system of BPS states in which are supposed to represent elementary strings. So this in fact is an old problem, but let me review what the problem is. Okay. So we'll be considering heterotic string theory compactified on a 10 minus d-dimensional torus. Okay, so now I'm in a specific system, specific string theory. So this describes a theory in d non-compact space-time dimensions. Okay. And the spectrum of the string contains states that carry electric charges under various U1 gauge fields in the theory. These are elementary string states, so no magnetic charge. Okay, only it carries only electric charge. So, and we will denote by Q the charge vector. Okay. And a subset of these states are invariant under half the supersymmetries of the theory, and these are therefore BPS states. Okay, in fact, these states were introduced by Doublecar and Harvey almost, I think, 40 years ago now, maybe a little less than 40 years ago. Okay, so the point is that as we go high in charge, okay, these states start having large degeneracy, okay, and also large index. In this case, in fact, one can show that the microscopic calculation gives the same result for degeneration and index. Okay. And the question is it possible to describe them as black holes carrying the same charge vector? Okay, this is in fact the probably the first system where this question was studied, and this is also the gave rise to the birth of the fuzzball program. Right? The first fuzzball solutions were constructed for this two-charge system in heterodyc string theory. So first, let me give the microscopic formula for this SBPS, okay, because it's very explicitly known. Okay, so here is the formula for SBPS. C is just some arbitrary positive constant. The result doesn't depend on C. Okay. And did I say what Q square is some, yeah, or maybe I have said it here. Yeah, Q square is some particular quadratic function of the charges, okay, which is a T-duality invariant combination of the charges. So right now it's just enough to know that it's quadratic in charges. Okay. So e to the SBPS is given by this formula over here. Okay, eta of tau is the Dedekind eta function, which is explicitly given here. Okay. So roughly one can say that e to the SBPS is given by the Fourier expansion coefficients of this function, eta tau to the minus 24. Okay. And indeed we can get exact result for any Q square from this, right? You just expand it out and read out the Fourier expansion coefficients of eta tau to the minus 24, and that gives you the result for e to the SBPS for that particular Q square. But more importantly, one can also find an asymptotic formula. Okay, how does this function behave for large Q square? Okay, and that is done by doing a saddle point integral of the tau integral. Okay, and this is the answer. What one finds is that for large charges, the SBPS grow as 2 root 2 pi times square root of Q square, and then there are corrections. So the first question one might ask is it possible to compare this with BPS black hole entropy carrying the same charge? Okay. And indeed this has a very long history, okay, spanning 10 years or more. Okay. But you are not going to review this today. Okay. So today we are going to change the question. Okay. The question will be, is it possible to compare SBPS, okay, with this combination over here, S world plus 2 pi ij at omega equal to minus 2 pi I over beta, because this is what is supposed to calculate the index from the gravitational path integral. So let's try to first do a scaling analysis. So recall that we had some scaling property. Okay, this scaling property of course works only for the Bekenstein-Hawking formula. So let's first write the Bekenstein-Hawking formula to see what we get. Okay. So Bekenstein-Hawking formula, which includes only two derivative terms in the action, tells us that M, Q and J scale like this, and the black hole entropy scale like this. Now we have seen that the microscopic result tells us that the black hole entropy is given by this, or the index is given by this, okay, which scales as lambda to the d minus 3, because Q scales as lambda to the d minus 3, and Q square is just a quadratic combination of the charges. So let's compare this with what we expect from the macroscopic side, S Bekenstein-Hawking plus 2 pi ij. This scales as lambda to the d minus d minus 2. This scales as lambda to the d minus 2. So one would expect that this combination will scale as lambda to the d minus 2. And now we see that there is a contradiction, okay, because this is much larger than this, okay, for large lambda. Okay, so given this, okay, the next thing one can do is to just calculate and see what we get. Okay. So this is a somewhat dense slide, but let me just try to draw your attention to the important points. Okay, that important results from this are really here. Okay, but let me just say what I have done here. So I have written down the action. This is the action of the low energy supergravity. Okay. CD is just some constant, right, which is also identified as 1/16 pi g Newton. Okay. G is a string metric, string frame metric, g mu nu. Right. So phi is the dilaton. Okay. G is a string frame metric. This is of course the standard Einstein-Hilbert term. This is a kinetic term for the dilaton. Okay. Here M is a matrix valued scalar field, right? So M is in fact 36 minus 2d times 36 minus 2d matrix valued scalar that is subject to this condition over here. Okay. And L is a diagonal, fixed diagonal matrix. Okay, so it's just enough to know that you have a set of scalar fields which are captured in this matrix M and its kinetic term is given by this. Okay. Then we have the two-form field, right? B mu nu, whose field strength is a three-form field H. Right, this is the kinetic term for the two-form field. And we also have a set of gauge fields, okay, and this is the kinetic term for the gauge fields. Okay, so the gauge field kinetic term you can see depends on the scalars.
So this is heterotic supergravity in?
Yes, just heterotic supergravity.
In how many dimensions?
In 10 minus, in d dimensions, right? 10 minus d is a number of compact dimensions. Okay. Now fortunately we know of a black hole solution, rotating charged black hole solution. In fact, the most general rotating charged black hole solution here is known. Okay. But here I have written down the corresponding solution by setting beta omega equal to minus 2 pi I, right? Because in that setting, the solution simplifies. Okay. It's still rotating, right? As you can see from this cross term, d tau d phi. Okay. The metric looks a bit complicated, right? Now the important point is that this solution is parameterized by three parameters, m0, beta and alpha, b and alpha, right? Roughly m0 is the mass parameter, right? Alpha is an angle that, not an angle, it's a real parameter that characterizes the charge, right? I have not written down the expression for the gauge fields, but alpha appears in the expression for the gauge fields. And b is the angular momentum parameter. Okay. So this metric has a horizon at rho equal to b, okay, and once you say, okay, so horizon at rho equal to b, so you can calculate the entropy by calculating the area of the horizon, okay, because you are still using the Vacant-Snocking formula. So the important parts, as I said, are here. So this is the expression for the charge, right? In particular, this quadratic combination of the charge, or square root of the quadratic combination of the charge that I introduced earlier, that from this expression for the gauge fields you can read out is given by this formula over here. Okay. Omega k in my notation will be the volume of the unit k sphere. Okay. In the same notation, the black hole entropy or the Vacant-Snocking entropy is given by this, okay, and J is given by this. Okay. And one can verify the scaling properties that I mentioned earlier, okay, because m0 is a mass parameter that scales as lambda to the d minus 3, and so Q also scales as lambda to the d minus 3, right, as you had said, and B scales as lambda, right. So you can say that m0 scales as lambda to the d minus 3, B scales as lambda, so the entropy indeed scales as lambda to the d minus 2. Similarly here, again the m0 B combination appears, J scales as lambda to the d minus 2. But now you see that when you calculate this, Vacant-Snocking plus 2 pi ij, you get 0. Yes.
I'm a bit confused. So the J is some angular momentum, or what?
Yes.
And in what sense can I think of? So that solution there is Euclidean or Minkowskian?
Euclidean.
Is Euclidean. I see.
Yes.
So you had the real angular momentum, honest to goodness Minkowski angular momentum, Lorentzian angular momentum, and then you continued to Euclidean, and this became an imaginary parameter.
Yes. Well, it became imaginary because I have said take this B. In fact, okay, I set omega equal to beta omega equal to minus 2 pi I, right? So
I see in the Euclidean calculation.
So that put an I, right?
Okay.
And so that's the reason we got this factor of I over here.
I see. But if I'm to take this solution and to interpret it in a Lorentzian fashion, can't I say that the black hole entropy is just given by the J, or
Not by J? No.
Is there some formula for the entropy of the black hole?
That's this one. This one.
Baker's Snapper.
But if I'm in Lorentzian signature,
Yeah, it's the same formula.
but can't I say the expression S black hole plus 2 pi j is equal to 0 in Lorentzian signature, doesn't tell me that the black hole entropy is just given by 2 pi times j or something?
Yes,
or?
minus 2 pi ij.
No, in Lorentzian. So in Lorentzian there's nothing imaginary, there's no j which is imaginary.
Well, the point we have set omega equal to minus 2 pi I by beta, right? So this particular solution in the Lorentzian geometry is for complex angular momentum. It's imaginary
It's for
angular
complex
momentum.
angular
Yeah.
momentum. Okay.
So this is not a regular black hole solution in Lorentzian space. In the Euclidean space, it becomes real, right? But in Lorentzian space, it will become a complex solution.
Okay.
Because you see, if you take a Lorentzian black hole with the regular Lorentzian black hole with real angular momentum, then the Euclidean space, the d phi dt term becomes imaginary, right? But now because you have set omega equal to minus 2 pi I over beta, right? I'm taking j to be imaginary.
I see.
So in the Euclidean space, it's a regular real solution. Right? But in Lorentzian space, it will correspond to imaginary angular momentum.
Okay, thanks. Yeah, Samir first and then.
If you could put everything real in Lorentzian space, but then you get a ring-like naked singularity. It's just a Kerr-Newman black hole.
But do you have the same formula?
Yeah, it is exactly the same formula because you can just set j to ij, right? Or j to multiply j by I, and you'll get the formula.
And the geometry becomes strongly curved near the horizon?
Well, I'm coming to that,
Okay.
right? Not near the horizon. I mean, horizon in fact looks regular, right? You can see that scaling is such that most of the horizon is completely non-singular.
So the Lorentzian solution, the regular one, the one you're talking about, the Lorentzian solution is some heterotic string with some angular momentum, and there's a lot of angular momentum. And
If you put real angular momentum,
sorry,
if you put
if you
real
put
angular momentum,
yes,
yeah, it's a highly spinning object.
it's ICTS, and this is like the Kerr entropy, which goes in the limit when j is large becomes j.
Well, you are not taking j to be large limit, right? See, j in a Lorentzian solution also you will normally scale j as lambda to d minus 2. And that's the regular scaling that we do, right? M and A scale in the same way. In the Lorentzian solution, the mass parameter and the A, right, in 4 dimensions, for example, right? They scale in the same way. So it's exactly the same scaling that you are doing. So it's not particularly highly rotating in the Lorentzian geometry.
I see. It's not highly rotating.
Yeah, it's Kerr-Newman.
But
Yeah.
where's the charge in the entropy formula then?
Which
I see.
formula?
So in the Lorentzian solution there's an entropy. So I mean this S black hole plus 2 pi j 0 has a Lorentzian version.
Yeah, there's a Lorentzian version indeed,
But
where
then
j
why
is
does
imaginary, right? For imaginary j.
Yes, but then I just don't understand the Lorentzian solution. Is it a two-charge solution? How can I say the entropy is equal to j? I mean, I just don't understand what's the Lorentzian.
It's a two-charge solution, but not extremal. It's a two-charge non-extremal solution. Horizon is regular.
Okay.
Well, most of the horizon is regular.
But
It's a rotating solution in carrying 2 charges.
and the entropy doesn't depend on the 2 charges, just depend on j?
For
Normally
when you
when I have
said beta omega equal to minus 2 pi I, right?
Then you fix the j in terms of the
Yeah,
2 charges.
exactly.
Okay.
Yeah.
That's the thing. Okay.
Yeah.
I was just wondering how I got.
Yeah.
Okay, thanks.
Yeah. Okay. So let's proceed. Okay, so first we see that we have survived the inconsistency, right? Because if this was non-zero, s plus 2 pi ij, it would have scaled as lambda to the d minus 2. Okay? But we have seen that the expected microscopic result scales as lambda to the d minus 3, right? So the fact that it is 0 at least has saved us from immediate inconsistency. So here you have, this is what we have, S BPS goes as lambda to the d minus 3, S black hole plus 2 pi ij goes is 0. So to proceed further, we need to recall that string theory has had derivative corrections, of course, to the low energy effective action. And next order terms will contain 2 extra derivatives. So those 2 extra derivatives will have to contract with the inverse metric. And because the metric scales as lambda square, when you contract the 2 extra derivatives with inverse metric, we will get an additional suppression of lambda to the minus 2. So previously,
this was going as lambda to the d minus 2, j was going as lambda to the d minus 2. After taking into account the next order corrections, okay, we would expect that this was 0 to the leading order. So next order corrections will change it to lambda to the d minus 4. Because S black hole gets a correction of order lambda to the d minus 4, J gets a correction of order lambda to the d minus 4. So this will now be of order lambda to the d minus 4. Okay. But that is a contradiction because we are looking for an SBPS which is lambda to the d minus 3. Okay. So while we survive the first inconsistency, we now stare at a second inconsistency. Right? Now the gravitational entropy computation gives you result that is less than the microscopic calculation. Now this argument holds, okay, provided the geometry is smooth. Right? So the higher derivative corrections will not be able to cure this problem if the near horizon geometry is smooth. But if the geometry is not smooth, then this argument does not quite work, because there may be regions where the curvatures are large and the derivative expansion breaks down. Okay. So we should ask, is the geometry smooth? Okay. Now when we inspect the metric closely, we find that the metric is in fact singular over a subspace of the horizon. Okay. And for d equal to 4, this subspace is basically north and south poles. Okay. So the idea now is that we should then study the solution near this subspace in the large lambda limit, because away from this subspace the metric is smooth and there is no hope that the higher derivative corrections will give you the contribution that you are looking for. Right? Higher derivative corrections will be smaller.
And these higher derivative corrections are coming from alpha prime corrections?
Alpha prime, yeah. I'm going to argue why it's coming from alpha prime corrections.
And is at this singularity, what's happening to the dilaton?
It's blowing up.
Blowing
it's going
up.
to strong. It's going to e to the minus phi is going to infinity. So which means you are going to the weak coupling limit.
Weak coupling limit.
Yes.
Okay.
So it's consistent to keep only the alpha prime corrections. Okay. So let me just show you why the solution is singular. Right? So this solution looks regular for most of the horizon, but you see that rho equal to b is the horizon, right? And at rho equal to b, this factor is b square sine square theta. Right? And at theta equal to 0 and pi, this vanishes, right? And that's the reason why the solution is singular at the poles, right? But it's non-singular everywhere near the horizon, and I have not written down the expression for the dilaton here, but e to the minus phi actually blows up. This will become clear when I write the solution near the singularity. So here is a solution near the singularity. Okay. And I have written it in a modified, different coordinate system. Okay, that makes some of the features of the solution clear. Okay. So here is a metric. Okay, now I have written down everything, right? The gauge fields, the three-form field e to the minus phi. So this is the complete solution near the singularity. Okay. This subscript E basically means that you are using a Euclidean. Okay, I mean this A is defined as I times the original gauge fields, so that everything looks real, right? But solution, the gauge fields are in fact purely imaginary. Okay, as is usually the case when you do a weak rotation. Okay, now the key feature that I want to point out here, okay, which is going to be important, is you see that all dependence on the parameter have basically gone away from most of the solutions. Right? Most of the solution is completely universal. R, theta, phi, and tau are the coordinates. Okay. The only dependence on the parameters come once here. Okay. This is the metric on the d minus 4 sphere. Okay. There is a b square that is multiplying this. Okay. B is a large number. B scales as lambda. So in the lambda large limit, this is large. So it's a large sphere that becomes a factor of the geometry. And the other dependence comes from the expression for e to the minus phi. There is an overall multiplicative factor that comes here. Okay. And so the solution is universal except for a separate sphere of large size, as I said here, and an overall factor in e to the minus phi, which scales as lambda. Okay, and because lambda is large, e to the minus phi is large, so the string coupling is small. So here is the solution, okay, written in small print. So the way to interpret this solution will be that this provides a boundary condition at large R, because at large R the supergravity approximation is good and this is the form of the solution. Okay. But once you go to finite R, right, the curvatures become of order 1. Okay. And that's where the stringy corrections become important. Okay. The loop corrections are not important because the string coupling is small, right? E to the minus phi, as I said, is large, so which means string coupling is small. Okay. So you have to worry about how the alpha prime corrections will change the solution at finite R. Okay. And in principle, if you want to do the alpha prime correction, you have to take into account all derivative order, right? Because curvatures are really of order 1, so you cannot make any approximation. Nevertheless, we can say something about the solution, because you see that the dependence on the parameters are very limited, right? One is as an overall factor in e to the minus phi. Now the stringy alpha prime corrections, right, are not sensitive to an additive constant in phi, okay, because this just gives an additive term in the dilaton. So the alpha prime corrections are not going to be sensitive to this. Okay. And this is another place where the parameter b appears, but this again is a very large sphere, right, almost flat, right, which is factored from the rest of the geometry. Okay. So again, this is not going to affect the stringy corrections to the rest of the geometry to leading order. Okay. All that will give is just the volume factor, right, which is the volume of the d minus 4 sphere with radius b. Okay. So from this analysis, we can argue that this combination, after taking into account the higher derivative corrections, okay, the higher derivative corrections in the smooth part of the horizon are not important, because those will be down by higher powers of lambda. Okay. So near the singularity, when you take into account higher derivative corrections, it will have the following form. Okay. So first of all, there is this factor CD, right? This appeared as an overall constant in the action, right? So this will appear in the expression for the entropy. Then e to the minus phi has this form, right? The action has e to the minus phi as a multiplicative factor, so you'll get this factor from here, from the e to the minus phi. And then the volume of this d minus 4 sphere, which is b to the d minus 4 times the volume of the unit d minus 4 sphere. Okay. And this should be multiplied by a completely universal constant. We don't know what this constant is, but this is independent of all parameters, and it's also independent of d. Right? Because you can see that the part of the geometry that is relevant, right, is this 4-dimensional part, okay, and that has no dependence on t. So you expect
5 minutes?
5 minutes, okay, yeah. So you expect that k is unknown, but it's completely universal, okay, and let's see what we can get from there. So here I have again collected the formulae that we have already seen. So S world plus 2 pi ij we expect to be this formula, to be of this form. This is the same as what I wrote here. Okay. And square root of q square, if you remember the expression that I had written down earlier, that is given by this for the solution. Okay. So far we have not said anything about omega k, right? Expression for omega k, it says the volume of a unit k sphere, but now we need the expression for this, okay, which is given here. And using this, we can see that we can now express S world plus 2 pi ij in terms of q square root of q square, because most of the factors are the same, right? You can see. Okay, except that here you have omega d minus 4, here omega d minus 2, and then there is a d minus 3 here. So after you do all that, okay, we find that the factors of d all cancel, and we get this expression over here. Okay. So you can compare this with what we got from a microscopic analysis, which is here. Okay. And we see that both formulae are independent of d, and also asymptotic values of phi and m. All parameters have disappeared from both formulae. Okay. And so at this stage, we can see that they have the exactly same structure, and they would agree if k is equal to 8 pi square. Okay. And I should just add that the same result, one can argue, holds for any other compactification of heterotic string theory that preserves 8 or more supersymmetries. Okay, I have done this analysis for toroidal, but you don't have to restrict to toroidal compactification. Okay. Now, if we want to find k from first principle, we need to determine how higher derivative corrections modify the near horizon geometry and the black hole entropy, okay, which we do not know how to compute, but I'll say what is known. Okay. And here I can relate this to the work of Chen, Murthy and Turiachi that I mentioned, okay, and this, I think Samir will talk about this in the afternoon. Okay. They consider the same system, okay, but specifically in D equal to 4, but they use a different language. They use a language of n equal to 2 supergravity. And they show that if we include a special class of higher derivative terms, okay, which are the F terms to correction to the effective action, okay, then it makes the solution regular. Okay. Now, in principle, with that solution, one should be able to calculate this combination. Okay, this has not been done from first principle. They have a guess for what this formula should look like. Okay, and I believe that it should be possible to calculate this also from first principle. Okay. But with that guess, the result indeed does reproduce the correct coefficient k. Right? That k equal to 8 pi square is exactly what comes in their language. Okay. And so since our result shows that k is dimension independent, okay, if what this shows is that k has the correct value for all d under the same assumptions that were used in their paper, okay, even though that analysis was done in d equal to 4. So here are the open questions. Can you justify the assumptions of their paper? Okay. Or better still, is it possible to construct an exact worldsheet CFT that describes the universal geometry near the singularity and compute the entropy from first principles? Right? Because you really have a completely universal geometry, right, given by that basically the 4D geometry that I described. Yeah, this one. Right? This is a completely universal geometry. These are just irrelevant parameters as far as the worldsheet theory is concerned. Okay. And so one should be able to see if there is an exact worldsheet sigma model that completes this for finite R.
If you didn't have a 4 instead of the r squared, it would be a smooth geometry, right? If I mean the
yeah, I think so. Yeah, yeah.
So it's just the 4 which makes your conical. So your 3 sphere. So you have a 3 sphere between theta, phi, and tau, which is shrinking, but the coefficient of the 3 sphere is not the right one. It's
exactly.
actually shrinking with the 4 instead. It would have been flat space otherwise.
Exactly.
Okay.
Yeah.
But it's not a typical conical singularity. This is some weird singularity.
Yeah, it's a weird singularity. And the point is that there are also stress tensor blows up because of this phi and h. Right. Mm-hmm. You see phi, there is a dilaton goes to, it's going to weak coupling, right? But phi goes as log r, right? So the derivative of phi goes as 1 over r.
Oh, I see. So that's unhappy. Okay.
Yeah. So there is a stress tensor singularity near r equal to 0. So it needs some modification.
Okay, thanks.
Okay, so this is basically the end of my talk. So I'll just, I think, have one more slide. Since this is a conference on microstates, right, I thought I'll just add this, okay, that any proposal for supersymmetric black hole microstates, okay, must produce non-vanishing index, because we really do know from microscopic counting that the black holes carry non-vanishing index, and log of the index is of the same order as entropy. In fact, it's exactly the entropy to leading order. Right? So if you are trying to construct microstates of a black hole, right, it will be good to make sure that it has non-zero index, because then you can be sure that those states are there. Because otherwise, there always remains a possibility that these are artifacts of working at some spatial points in the moduli space and will disappear once you go to a generic point. So this, I would say, is the lesson from this, because we now know that gravitational path integral can actually calculate the index, and so it will be better if one can also look at the index from the microscopic side. From the microscopic side also calculates the index, but this geometric construction, right, fuzzball-like construction, right, it will be good if one can also compute the index from those constructions. Thank you.
Further questions, comments?
In order to avoid this contradiction with the scaling argument, you just needed that k was non-zero, but to get a further match, you had the specific value.
Yes.
Is there some simple first principles argument that k must be non-zero?
No. At least I don't know of any first principle argument. Yeah, so k could be 0, in which case, if k is anything other than 8 pi square, there will be a contradiction. Right? Yeah. Because at this level, we already know the microscopic result.
Yeah.
Yeah, so I don't know why I don't know of any argument why k should be non-zero.
when you have the singularity at the North Pole and the South Pole, can you dualize yourself into some other duality frame when it becomes nice and happy, or is it? I mean,
Yeah.
I've
So the
never
point
seen
is
such
that
beats before. So.
the dilaton, the string coupling is going to weak coupling at those poles, right? If you go to another duality frame, then string coupling will become strong.
I see. You're heterotic, so you cannot
Yeah,
dualize,
one can
you cannot
heterotic.
dualize yourself.
Yeah, if you try to dualize it, the string coupling will become strong at those regions.
So it's really a weak coupled heterotic singularity.
Yeah, it's a weak coupling heterotic singularity. So that's why it's a singularity that should be treatable by sigma model.
Mm-hmm.
Okay, then if there are no further questions, let's break for lunch and let's thank Ashoke again.
Thank you.